Alright, so today we are going to discuss HDFS. This is the main component of Hadoop ecosystem. So I would like to go into the detail about the basic building block of Hadoop called HDFS. Alright, so imagine you have 100 terabyte of data and you want to store this 100 terabyte of data somewhere. Where would you store such kind of data? How would you store 100 terabyte of data? Or let me rephrase the problem that you decided you're living in a hostel or you're living in a society where all of you decided to build a centralized storage which can store the movies up to 100 terabyte. How would you build such kind of system where all the people in your society or in the hostel can watch the movie and store the movie in this 100 terabyte store? How would you do it? What you do is you buy 100 hard disks or 100 drives, each with the storage of 1 terabyte data, and connect them somehow in the network. And when you connect them in the network, you mount these hard drives on some central network shared computer, or maybe multiple such folders in the network. Okay, so that when you access folder 1, it's pointing to the drive 1, and when you access the folder number 2, it's accessing the drive 2, and so on. All right, now do you see any problem with this kind of system? For a record, before HDFS, we actually organized data in this form. And you would be surprised to know that most of the prestigious institutions as of today use a similar architecture where they connect many computers together, put a lot of hard disk inside these computers, and then mount these hard disks on a common folder. All right, and also before you say that one of the problems with these is that there is no backup. Okay, so traditionally what we used to do is have 2 hard disks instead of 1 hard disk, and one of them is just a copy of the another, so that in case one hard disk goes corrupted or there is some hardware problem with one of the hard disks, there is a backup of that hard disk on the same computer. Now, do you see any problem with this kind of structure? Okay, let me come back to the question again. So we took 100 hard disks, connected them in a network, or maybe we took 200 hard disks, connected them in a network such that on each computer there are maybe 4 hard disks catering to 2 terabyte of data, because each disk is a copy of another. A redundancy of 2, that's what we did here. Okay, so do you see any problem with this kind of network? First, the problem is failover and backup. There's a difference between failover and backup. Failover means if something fails, something else will take over. While backup means in case something goes offline or something gets corrupted or get damaged, we have a backup from which we can recover the data. We'll not lose the data. But there will be a human intervention required to bring the system back to life. Okay, so this system does not have failover or backup. For example, one of the computer is burnt and both the hard disks are gone, then the data is gone, right? Although by putting, maybe we can put redundancy on each hard disk by using a RAID. RAID is RAID, redundant array of independent drives. Okay, so if you put RAID means there are RAID 2, RAID 1. RAID 1 means there are 2 copies of each drive. Okay, there's one backup available. So even though we could try to do RAID, but RAID is not really greatly successful. And next is failover. What if the machine goes down, there is nobody else to cater the same data? Next problem is, how would you distribute the data uniformly? Okay, since we are putting data, so what we'll do is we'll say, let's say that we have got 100 drives. We dedicate first two drives to A, second two drives to B, and so on. Now again, there are chances that there are too many movies starting with A, or there are too many movies starting with S. While so it'll be always a difficult scenario to distribute the files equally. Next is this the best value for money? 1 terabyte hard, you might be having the resources already in your organization. Is this the best value of money? We might have hundreds of hard drives, smaller size, already available. Can't we utilize those? If we try to utilize those, then we'll have too many hard disks in the network, and again, the manageability goes haywire. We will have to manage the data in this new small hard disk as well. Or because we can't, if we have a smaller hard disk of say 20 GB, we can't store the data bigger than 20 GB file, right? So the hard disk completely goes waste. If we are trying to store a file, say we are trying to store 80 gigabyte Blu-ray, right? 80 GB Blu-ray we are trying to store in this file system, and our hard disk is smaller than that. We can't store it. Or a hard disk has 70 GB space left. We won't be able to store 80 GB hard. So that space is left. Okay. So we will not be able to distribute data uniformly, and this is not the best value for money. What about increasing accessibility? And what about scaling out? Today, we need 100 terabyte space. Tomorrow, we might need 110 TB of space. Or tomorrow, we might need 150 terabyte of space. Then, does your solution requires too much of effort for migration from 100 TB to 150 terabytes? Okay, this is called scaling out. We are not scaling up, we are scaling out. Scaling up means instead of 1 terabyte, we remove 1 terabyte and put 2 terabytes. Okay, that again is too much of headache in this system. All right. Now, so what exactly is the solution? In simple word, I'm trying to sell to you that HDFS will solve the problem as of now. Although there are few more systems on the lines of HDFS, but that we can discuss later. All right, so let's try to understand. I'm going to go step by step. First of all, the most important thing to understand about HDFS is it's composed of many computers. So we connect many computers together. We install HDFS services on these computers. One of these machines is designated as name node, while rest of them we designate as data node. Okay, so in the network there is one name node and rest are data nodes. Also, please keep in mind that you are free to install data node as well as name node on the same machine. And what are these in terms of computing? These are not hardware. Instead, these are processes. Just like a mail server running on your computer or somebody's server. Okay, in a similar way, these are computer programs. Name node is a computer program, is a network service listening on a particular port for the traffic coming in. Okay, similarly, data node is a process running on a computer listening for incoming traffic. So HDFS is composed of two kinds of services, name node and data node. Only one node is designated as name node, while rest are data nodes. Name node is like the king or the central agency. As some of you had pointed out, that somebody has to keep track of which file is where. If we are storing it in the previous architecture where there were so many computers, we have divided the files into the multiple computers. Somebody has to keep a track of what is where, right? Somebody has to keep journal, this kind of accounting, that which data is located on which computer and which hard disk. And data node store the actual data. All right, so you can think of admin node as just the entry in an Excel sheet, and you have marked that, okay, first this data is on this computer with this IP address. This data is on this computer and that IP address. All right, so that is name node. So name node keeps the index of what is where, and this is called metadata. Metadata means name of the file, name of the folder, and for every information, like for if you it is a folder, who is the parent folder and so on, the full information about the file system, about which file, which folder, how many folders, how many files, what's the file size, what's the name of the file, and what's the attribute, like who is allowed to access which file, all of this is called as metadata, and all of this is maintained by name node. Okay, name node is a service. Okay, as I told you, it's like a Windows service which is running in the background, listening on a particular port for the traffic to come in, just like an email server which is listening on a particular port and waiting for the traffic to come in, similar to the HTTP web server which listens to 80 port. Okay, email server listens to 25 port, and here the name node listens on 8020 port, and data node listens on 8030. So basically these are just the services listening on certain ports. All right, name node keeps all of the data in the RAM, although it keeps a copy in the disk. But whatever is the metadata, it'll keep in the memory so that it can quickly serve. Now you can think of this structure that name node should be run on a computer which is having big RAM, big memory, and data node should be run on a computer which has got bigger disk. All right. Now let me take a step further. While storing data into data node, the files are cut into 128 MB blocks. Except for the last block, all blocks would be of the size 128 MB. The last block might be lesser than 128 MB, but it only stores the amount of data which is there. In case you have 130 MB data, there'll be two blocks, one of 128 MB and second one is of 2 MB. Second block will not consume 120 MB storage. There is no buffer or offset. Okay, so the files are broken into the blocks of 128 MB. Earlier, and in some of the systems still, this size is 64 MB. That's a design decision which Hortonworks has taken. So we are going ahead with 128 MB on our CloudxLab. Okay, on our CloudxLab, the default size of a file is 128 MB. Default size of the block. So we break the file into the blocks of 128 MB. So if we have 1 gigabyte file, there'll be 8 blocks, 8 pieces of this file. Okay, so why do we do that? It helps us fitting big files into smaller disks. Second, it leaves less unused space on every data node. Okay, and it optimizes the transfer of the files. And moreover, in case there is one file which is distributed on 10 blocks or 10 data nodes, whenever user is accessing the file, the load will go to 10 machine, not only one machine. And that's how it distributes the load to multiple machines. Okay, so we talked about few things. First, HDFS is composed of two different kind of services. One machine has been designated as the master and called name node, and rest of the machines are called data node, where data node stores the actual data, what is inside the file. So data node does not know the name of the file, while Name node does not know what is inside the file. So that's how it is. Everything to do with file name, folder name, attributes, and everything, folder structure, and everything, which is not the actual data, which is the metadata, is stored on name node. Okay, so then we talked about that each file is broken down into blocks, and that's very useful. Just like when you download a big movie using a torrent, that file is broken down into pieces, and these pieces come from multiple machines parallelly. And it helps downloading parallelly, as well as it helps us balancing the load. So there are many more benefits of breaking down a big file into blocks. Okay, next is it's like building a house with small bricks, because you can't build just a big house with a very big bricks. So although that's a bad analogy, but it should give you an idea. Second is every block has multiple copies. Okay, so we have broken down a big file into small blocks, and every block has got the default copies as 3. You can change this default setting of HDFS to anything you want. But I would recommend personally that keep it 3. I'll give you the reasoning behind keeping 3 copies. Okay. So every block, whatever we have sliced it earlier, gets 3 copies. Okay. One on one node, second on another node, and third on some other node. Generally, first 2 copies are on the same rack, and the third one is off the rack, some other computer in the network. And rack means an almirah in which you stack the computers such that these computers are in the same local area network. Okay, so 2 computers which are closest to each other are generally connected in the rack. So an almirah is called a rack in a data center. So first 2 copies are on the same rack, and third one is off the rack. All right. So each block has multiple copies, and this is called a replication factor. By default, the replication factor for a file system is 3. You can change the replication factor of each separate file, as well as you can set the default replication factor of the file in a file system, so that if you don't like the idea of 3 replication factor for each file, you can set it to something else. As well as if for some file which are not very important, you can change it to lower, and for some files which are very important to you, you can increase the replication factor. All right, and in case one of the data node goes haywire or is get burns down, you have 2 more copies of each block that get lost, right? Because every block has 2 more copies somewhere on another computer, and in case one of the data node goes down, you have 2 more copies lying around in somewhere in the network. At that point of time, name node will instruct those nodes having those 2 backup copies to start copying them, such that every block again regains the 3 replication factor. All right, so we talked about replication, we talked about blocks, and we talked about name node and data node. All right, so one more thing I would like to say. All right, so as it sounds that the user will only talk to name node, that's what we studied so far. In all our architecture diagrams, everywhere it was something like we choose a leader and leader talks to everybody in the network. No, in this case, no. Name node is only accessed once by the user when they're looking for the file. And afterwards, once the user gets all the information about which block is on which machine and which copy is on which machine, then the user directly goes to the individual data node. So you can see here, the user for the first time comes to the name node and says, hey, I want to create a file or update a file. Name node says, hey, don't bother me. Go directly to the data node. Either you want to read or write, you talk to the data node, and once you are done writing, just let me know. In case you are reading, don't come back. and don't bother me, I'm a very busy person. Okay, the reason is name node is a high traffic one. The reason why name node keeps everything in the RAM is so that it can cater to all the needs. And HDFS makes sure that no two people try to intervene in the same file at the same time by the use of a singular name node. If there are multiple name node, what would happen is some user went to one name node, some other user went to another name node, and effectively they will corrupt the file system. Here, there's a strong consistency. There could not be two writers at the same time. Name node will block it. All right. So the client driver comes to the name node and says, "Hey, I want to read the data." Name node says, "Okay, which file do you want to read?" This file. This file has got these many blocks. These blocks are located on these data nodes. Why don't you choose by yourself which copy of the block you want to read? And it's up to you. It's up to the driver whether it wants to read it parallelly or sequentially. Okay, and this is not done by you as a user. This is done by either the client you have created by writing the API or the command line you can use upfront. If you are building a video streaming service, you will read block by block, one block from one machine, and then stream that block to the end user. The end user will watch the movie, that particular block, and then you start reading the block from another machine, and so on. In case you want to quickly stitch the data, you might want to read all of this data together from all the machines. You might want to create your own driver. Okay, so this driver, the client driver, is generally the command line called Hadoop FS, or there could be the API or the web interface, okay, that you are using. So user uses client driver goes to the name node for first interaction to find out the metadata, and then goes to individual data node. So you can see that name node has cleverly avoided itself from becoming the bottleneck. All right. So what happens in case name node is shut down? Since name node is singular, and what if the hardware burns at the name node level? What happens in those cases? Okay, so name node keeps a backup of namespace, as in the full memory, as in what are the folders, what are the files, and everything. It keeps a backup copy of the whole memory image, along with edit nodes on two locations. It can keep that on two locations. It can keep in a local storage as well as in a network file system. So in case the name node goes down, you can get the data from either the network file system or maybe the local storage. So this is a bad way of recovery, because here you will have to have a manual intervention to bring back the name node. Okay, so that's the first way of recovering from the name node failure. It is a backup, but it's not a failover. Okay, the second one is called the secondary name node. Okay, in case of secondary name node is keeping two copies of the backup, one in the local storage, two copies of metadata in the local storage, although it keeps in the memory as well. So it keeps the edit log and the image of the memory, because the way most of these systems work is they periodically saves the complete image into the disk, and then as and when there is a change happening, it keeps on adding more and more records. Okay, those are called edit logs. So it's like periodically they purge the whole image into the disk, and afterwards all the changes that happening, it keeps on making entry in the edit logs. Okay, so these edit logs plus image, image as in namespace image, these two things can be stored on the local storage, as well as you could have something called secondary name node. But the problem with the secondary name node, though it sounds like it's ready to be served? No. It just you have to bring secondary name node up to the speed of name node, and then you bring it up. Otherwise, so you have to manually brought up the secondary name node to the latest image, and in case of emergency. Okay. All right. The best way to have better availability of name node is by using a backup name node or standby name node. It's called backup name node or standby name node. So name node, although it remains a single point of contact, it has a copy, a mirror image of itself called standby or backup name node. So this is another architecture, so you can choose any of the three. I prefer this one. You have name node and you have standby. In case name node goes down, immediately standby will be brought to life automatically. Okay, and the way it happens is actually quite interesting. This started happening in Hadoop 2.0. Okay, it's also called quorum general manager for high availability. So all the data nodes know about both of the name node as well as standby. Similarly, name node knows about standby. So every time name node makes a change, it informs the standby. Similarly, every time data node and wants to talk to name node, it also informs standby. So the job of keeping standby updated is of everybody, not only name node. So everybody who wants to update name node also informs standby. Okay, so this model is called quorum general manager, using quorum general manager. And the moment system guesses that okay, name node is down, immediately standby becomes the main point of contact. And this switching could happen using something called zookeeper, and there are few more models. All right, so now the fourth level of backup. Imagine, so this was up to the point where name node could fail. Now there could be another problem with the name node, and the problem is, what if the memory is insufficient? You have got too many files to store, and name node's memory is not allowing, and it's becoming the bottleneck. The RAM is becoming the bottleneck. So what do you do in that case? Okay, first, if you have too many small files, the best way to store in HDFS is club them together using a tar format or a zip format, and then store those all files in HDFS as a single file. Okay, or you create something called sequence file. It's a format provided by Hadoop, so that you can combine all the files into a single file, into something called a format called sequence file, and then you hand over to Hadoop. And Hadoop efficiently handles sequence file. So at any point of time, you can read a particular small file from a big sequence file. You don't have to unzip the whole file in order to read a small file which is packed inside a sequence file. So that is the first step. First step of handling too many small files in the HDFS is by concatenating all these files into something called a sequence file format. We will cover it when we talk about MapReduce. Okay, now in case you have got humongous file structure, okay, and there is no way to combine multiple files into a single file, then you might have to go for something called HDFS Federation. Again, it came in Hadoop 2.0, and it supports multiple name nodes. Okay, in case, and also the benefit of having multiple name nodes is sharing the load with multiple machines. And the way it happens is we maintain something called mount tables. The client library is responsible to maintain the mount tables. Okay, so client library will read from config that which folder belongs to which name node. Okay, which folder belongs to which name node, and accordingly route the request to the corresponding name node. So a mount table is a list of folders saying slash user is inside name node 1 and slash user 2 slash user 3 and everything else is inside name node 2. Okay, so mount tables is a list of folders with name node mentioned against their name. All right, so for example, in this diagram you can see that a request for my data 1 is routed by client library to name node 1, and the request to my data 2 and my data 3, these two folders is routed to name node 2. In ideal world, if I'm running this, I will have two name node having two different standby node. And the other important aspect to think about is this pool of data nodes. This pool of data nodes is common for both the name nodes. So name node 1, name node 2, utilizing the same pool of data nodes, storing their blocks, okay, and utilizing the same disk space. Because it's not the data node which became the bottleneck, it is the name node which became the bottleneck. Therefore, Federation allows multiple name nodes to serve the folder structure by utilizing same pool of the data nodes. All right. So this is the HDFS Federation. All right. So this mount table will look like something like this. It'll be okay. This goes to 192.168.1.34. Okay, and my data 2 would go to 35. This is our name node 1 and name node 2. Similarly, we might have name node 3 going to all these requests going to name. So this way, at the mount tables label, we could configure here. Mount tables will read this config from the HDFS configuration, and this is basically client library. It's not a server which is running. So if there are multiple users coming in, there'll be multiple instances of client library running in the memory and then talking to different name nodes. All right, so that's about the name node secondary failure. Now I would like to give you a little experience on hands-on. All right, under my courses you will see big data and Hadoop, and here you could see your login password. It's different from what you have for LMS. Okay, this is for CloudxLab. Now, the first service I would like to introduce to you is Ambari. Then we will talk about HDFS. Okay, so what is Ambari? Ambari is let me log in into it. I'm logging in as admin. Okay, so that I can show you a couple of more features. All right, so what exactly is Ambari? Ambari is a software which helps us install various components of Hadoop. So before you start installing Hadoop, what you do is you buy this hardware. Okay, you buy the hardware and then you install operating system on it, same operating system on all of it. And once you have installed the same operating system on all of this, the next thing you do is you establish, you install on one of the machines Ambari server. And on all the machines, we install Ambari agent. Ambari has nothing much to do with Hadoop other than helping us install Hadoop. The other way would have been that we would install Hadoop on all the machines. We ourselves will install Hadoop on the machines and then do all kinds of config on every machine. That kind of problems are solved by Ambari. All you have to do is install Ambari agent on all the machines and install Ambari server on any machine. Right now, we have installed Ambari server on H1. Okay, we have 5 machines, H1, H2, H3, H4, H5 right now, and we keep on increasing number of machines from time to time. Okay, so we use Ambari for installing our cluster. In the beginning, there'll be nothing here. It'll ask that on how many nodes you want to install Hadoop. You select the nodes, you say, I want to install Hadoop on these 5 nodes. On this node, I want name node. On this machine, I want data node. And this machine, I want rest of the services of Hadoop. You can see in the left hand side, these are the services which are there on our cluster. You have HDFS, MapReduce, Yarn, Hive, HBase, Pig, Scoop. These are the clients. You see, these are not the services. These are the clients. These are the commands that have been installed. These are client only. These are not running. These are not running. These are just, you know, what do you call passive commands. Whenever you want, you run pig and it will execute. Zookeeper is running, Falcon is running, Storm is running, Atlas is running, and all of these are running. We have Spark and everything. If you want to add one more service, you can do that. Let's say you came up with more hosts. You can go to add host here, and then here you can say add new host. It will ask for this wizard where you will enter the host name. You will copy the SSH key. SSH key is like sharing the password, and then we go next and then select what all services we want to install on that machine, and this Ambari would be able to install all those things. All right, now these are the services. If you want to see each individual service, let's say we select HDFS. So right now we have name node and secondary name node. We would be moving to standby very soon. Okay, we would be able to see here and say enable name node high availability. If we click on that, it will start the standby. Okay, we'll be doing that quite often, quite soon. Okay, right now it's only name node and secondary name node. High availability is not on. There are 5 data node, which means data node is stored on all machines. Okay, and you can see the name nodes. These are the services running on the first machine. All right. So this is a quick way of looking at the cluster. This interface called Ambari is generally for sysadmins. Okay. Now the one which you will be using is either Hue. Hue is a web interface to interact with Hadoop. Hue is the interface that you will be going to use more often. Okay, why? Because it gives you all kinds of interface. You can talk to Hive, you can write queries for Pig, you can write queries for Spark, and you can also design a Uzi job, and you can talk to HBase, you can see Zookeeper, and you can use Scoop from here in the UI without going to the command line. Okay, now let me show you the HDFS. HDFS is file browser. You can see inside the file browser. All right, for the file browser, you can see that there are too many files. For you, it might be completely empty. Okay, for me, these are the files existing in the HDFS, and this is the folder in HDFS. So the folder information is stored in the name node. All right, so this is a good way to interact with HDFS. It provides you this beautiful UI from where you can upload data as files. If you upload it zip, it will automatically unzip it, and you can also create the new folder or new file. So you could say create new directory or file, and then you can also search here. You could just say A, and it will search all the files containing A. Okay. Also, you can directly go to a particular folder. The data for you is stored in this folder called data/data, and for various tools, we have put all the data at a central place. Okay, we've installed all of this data is read only. You cannot modify it because all the users will be using it. Okay, you could always click home to go home. Okay, so right now this kind of folder structure does not exist on any of the machines because this metadata, this folder structure is just inside name node. Okay, so this is, let's say this is one file. This is one file containing hardly 1 byte. Okay, this file is actually one block. Okay, and so on. So this is the way to create a file. So you could also upload data from here. All right, let's try to see the things from console. All right, let's open the console. Either you could open a web console by clicking here, or you could also do SSH. Okay, if you could go to the terminal, you could also say SSH, and then SSH is a way to log in into a remote server so that you virtually reach there. Right now, I'm trying to reach to CloudxLab H5. So I'm saying SSH Sandeep Giri 9034 at h5.cloudxlab.com. Okay, it's asking for password. I copy the password and paste it. Now you can see that I have actually virtually reached that machine. And also don't get confused between LS, because LS is showing local file system. It's not HDFS. I am actually got transported to H5. Okay, H5 has its own file systems. All these machines also have their local file system, as well as they have a centralized file system called HDFS. So we could talk to HDFS using Hadoop fs minus ls. Okay, you can see that these are the folders which are coming from HDFS. Okay, so we could create a file locally. Let me create a file called 6fab, and I'm using VI. If you're not comfortable with VI, you could use something called nano. You can say nano 6fab. In here, this is my data. All right. Right now, when you say ls, you can see 6fab file created here. This is my file. I can say cat. Cat means printing the data, what is there inside 6fab. Okay, this is my local file in this H5. Local as in this machine in called H5. I'm right now logged in into H5. This is its local name. Okay, local intranet name. So you can see that we've created a simple file, but when you say Hadoop fs minus ls, you won't be able to find where is this 6fab. Is 6fab somewhere? I don't think so. Right now 6fab is not there in the HDFS. So okay, again, before I move forward, when you say ls, you are talking to the local machine. You're not talking to Hadoop right now. The way to talk to Hadoop is either you use this hue, okay, to query the files, or you use a command called Hadoop here. And Hadoop has got many commands. One is fs to talk to file system. Second is jar. When you want to execute your MapReduce logic, then you use Hadoop jar. So if you say Hadoop fs, okay, it shows you all the possible commands which are part of Hadoop fs. So you will say Hadoop fs change mode, change owner, change group, checksum, cat, and so on. There are so many things available. Right now, let's upload our local file. Okay, and to upload a local file into HDFS, we use either move from local or copy from local. So right now we are saying Hadoop FS, please copy my file from local to HDFS. And we say 6fab is my file. Now, when you refresh it here, the file has been copied to HDFS. You can see that 6fab has come here. Okay, this is my data. See that? This one is coming from HDFS, and this one is just this local file. I could also do SSH here. Let me exit from here and say, instead of E, I say D. D is H4 and E is H5. Okay. Now, if I say LS here, there is nothing in there. There's hardly two files. While on E or H5, when I say ls, there are so many files. Okay, but if I say Hadoop fs minus ls from H5 or H4, the file list will be same. I could say Hadoop fs minus ls because H4, H5 or whatever host we have, the Hadoop fs command is talking to name node and giving you the list. Alright,